Alright guys, this is the last video for chapter 4, which is derivatives of exponential and logarithmic functions. So I'm going to just write those out real quick for you guys. The derivative of the function e to the u is equal to itself, e to the u, but then times the derivative of u with respect to x. Okay, so if it's e to the x, it just is e to the x. If it's e to the 2x, it's e to the 2x times 2. Because then you take the derivative of the 2x. If you want to take the derivative of natural log of u, it's equal to 1 over u times the derivative of u with respect to x. So those are the first two. The third one now is if it's not base e but some other base. It's very similar to base e except for we need a natural log of a to convert it here. So if we have a to the u, it's itself times the natural log of a times the derivative of u with respect to x. So that's the added piece, is just when it's base a you need a natural log of a. And then finally, if you have the derivative of a log base a instead of log base e, we need a natural log of a on the bottom with the u. So it's 1 over u times the natural log of a. And then that's going to be multiplied by the derivative of u with respect to x, if it's not x already. So those are the 4 derivatives of exponential and logarithmic functions. So let's do a couple examples with these. Example 1, we have y is equal to e to the x plus x squared. I want to find y prime. So y prime is equal to, well, look, the derivative of e to the u is e to the u, so we're going to rewrite e to the x plus x squared. However, we have to multiply it by the derivative of what u is, and u is x plus x squared. So the derivative of this piece is 1 plus 2x. So that is the final answer. Okay, let's do another one. It's kind of like a piece within a piece for this next one. I want to know what the derivative. So find y prime. If we have y is equal to, and again you can actually use log properties to do this one. So hopefully you guys remember that log base a of a is 1, so you can actually simplify this ahead of time and bring the sine x down and you just get cosine x. However, I want to do this the long way to show you how you can use these. I'm going to call this my u for my log base a of u. So y prime is equal to, here's the log, it's number 4, it's 1 over u is sine of x. Nope, that's a lie. My u is the whole thing of a to the sine of x times the natural log of a, which is just a, okay, and then times the derivative of a sine of x. So now we have to go back to step 3 and figure out what the derivative of a sine of x is. Well, it's a sine of x times the natural log of a, because I'm not looking up here, times the derivative of sine of x, which is cosine of x. And sure enough, the a sine of x's cancel, the natural log of x's cancel, and you're left with y prime is equal to cosine of x, which we could have done using our properties anyway. Alright, so that's just using those properties. There is one thing that we can also do, and it's called logarithmic differentiation. I'll just write that out. And this helps you solve problems when, or take the derivative when the power is a variable. Okay. So here's the example we're going to do for that. If I want you to find y prime for y is equal to x to the x. Okay? Now we cannot do not use power rule. It's only for polynomials. And a variable to a variable is not a polynomial. So you cannot bring, multiply the x down and then do x to the x minus 1. That doesn't work. However, we do need to bring the x down. By the way, the restriction here is that x is greater than 0, so it works. So in order to bring the x down, to do logarithmic differentiation, we can natural log both sides. So I'm going to rewrite it now. We get the equation natural log of y is equal to, this comes in front, x times the natural log of x. Now we have pieces we know derivatives of. And this is actually going to be implicit now because this isn't just y equals anymore. We're going to have to take the derivative of y on this side. So the natural log of y, the derivative of this, so we're going to take the derivative of the whole piece. Derivative of that is 1 over y times the derivative of y, which is y prime, equals this. We're going to have to do a product rule because there's two things being multiplied. Right, so we have x times the derivative of natural log of x is 1 over x times the derivative of x, which is 1, so we're good there, plus the natural log of x times the derivative of x is 1. Okay, so we get y prime over y is equal to 1 plus natural log of x, multiply y to both sides, we get y prime is equal to y 1 plus natural log of x. You are not done here. When you solve for dy dx, you want it only in terms of one variable. Luckily, we know what y equals. What was y equal to at the beginning? Y equaled x to the x. So now we're going to sub that back in and say that our final answer, dy dx or y prime, is x to the x times 1 plus the natural log of x. And that's how you use logarithmic differentiation. You use that to bring the variable down and to help you out. Okay, I'm going to do one more problem actually. I thought I was going to be done now, but I decided to add one more problem. I'm going to start a new page though on here so I have room. This is another one using logarithmic differentiation, using log properties to help you solve. So, for example, if I give you the equation y equals 3x plus 2 quantity squared, 5x minus 1 quantity cubed, all over 7x plus 1 to the 4th, and this whole thing is raised to the 1/4 power. I want to take the derivative of this. Well, in order to take the derivative of this would be really, really bad. There would be a lot of chains and quotient and product rules, and it's a mess. However, when you have multiple pieces in a fraction, you can use your log properties to expand the expression and make it easier. It'll be a bunch of log derivatives then instead. Before we do that though, I'm going to just distribute this 1/4 into everything. So I'm going to rewrite this as y equals 3x plus 2 to the 1/2, because 1/4 times 2. This is going to become 5x minus 1 to the 3/4. And this is going to be all over 7x plus 1 to the 1st, so that's good. Alright, so now what we're going to do before we take the derivative, we're going to natural log both sides. And here's why we do that. We can now rewrite this as the natural log of y equals, remember when you have pieces multiplied, you can split them apart by addition, and then the last piece would be subtraction. So this becomes the natural log of 3x plus 2 to the 1/2 plus the natural log of 5x minus 1 to the 3/4 minus the natural log of 7x plus 1. Next step, we can bring these 3/4 and 1/2 in front. So the natural log of y is equal to 1/2 and then natural log of 3x plus 2 plus 3/4 times the natural log of 5x minus 1 minus the natural log of 7x plus 1. And now we can take the derivative of the whole thing. with respect to x. Derivative of natural log of y is 1 over y times y prime equals 1/2. The derivative of natural log of anything is 1 over the thing in the parentheses times the derivative of the inside, which is just 3, plus 3/4 times 1 over 5x minus 1 times the derivative in the parentheses, which is 5, minus 1 over 7x plus 1 times the derivative of what's inside, which is 7. Okay? So now, that's pretty much our answer, except for I'm going to move the y over, and then I'm going to re-sub in what y equals, okay? Actually, I'll do it in 2 steps, and then we'll be done. So y prime is equal to y times, this what becomes 3 over 2. Yeah. This becomes 15 over 4. And this becomes 7 over 7x plus 1. Okay, so that's kind of the final answer, but again, we don't want it in terms of 2 variables. So the last step, which is a little annoying, is just rewriting it with this whole chunk as y. So the derivative of that is equal to 3x plus 2 to the second, 5x minus 1 to the third, over 7x plus 1 to the fourth, all to the 1/4, times this piece up here that I wrote out already. Now I know it looks bad, it's a lot of writing, but do you guys hopefully see how easy it was to take the derivative once we split it up using our log properties? Okay, so that's another problem using logarithmic differentiation to solve a problem with many, many pieces. Alright, that's it.